Okay, a couple things before we get started. A couple of you have not turned in your questions on the Mulholland video. Those were included in an email I sent a week and a half, 2 weeks ago when I first told you to watch that video. Those questions are worth a couple of points on your first test, and in fact, if you do the math, it comes out to almost be a letter grade. So don't just punt a letter grade away by not doing those. I'll still give you partial credit by handing those in, but get those into me soon. Which brings us to the second thing we can talk about today, which is the test. We're about that point in the semester where I hate giving tests, and if there's anything I hate more than giving tests, it's grading tests. But they pay me the big bucks, and you pay the big bucks, so, you know, we got to do this stuff. So 2 weeks from today will be the first exam. I think that's October 6th. 2 weeks from today, it'll cover everything from the first day of class through whatever we get through next Thursday. Not on the lab, the topographic maps. There won't be anything on the maps on this first exam. That's a separate deal.
You said October 6th?
I think it's October 6th, yes. 2 weeks from today. I'll give you more information about the exam next week, but basically, well, I haven't made up the test yet, and I won't probably until a day or two before. It'll be some short answers, no multiple choice. I don't like multiple choice. Might have to calculate a thing or two, which is what we will get into today. So the only thing you really need to bring to class that day is something to write with and a calculator. Doesn't have to be a fancy schmancy calculator, because we don't do fancy schmancy math in here. We do simple math. And we're going to do some simple math today, actually. We're going to go into a little bit of physics today. And I don't know how many of you have had physics. If you haven't, that's cool. I assume nobody's had physics. And if you have had physics, then this should be some review. But we will present the physics in a way that kind of ties into the environment in the Earth. We'll apply the physics to the Earth, and hopefully it'll make a little more sense to you. For those that are taking the course online, when we get to the exam, I will have you sign into a Zoom session so I can see what you're doing, and once you're signed in, then I will email you the exam. You can write it out, take a couple of pictures, and then send that back to me by the end of class. So again, that's going to be 2 weeks from today, October 6th. First exam, mixture of questions, mostly short answer, maybe a couple calculation questions. And also make sure you get your questions from the Mulholland video into me for partial credit, because that actually counts a little on your first exam. Do you guys have any questions? Also, make sure you get the lab work into me pretty soon. You guys have till next week, but the sooner you get it in, the sooner you can start on the next lab. I'll send out the next lab, which is just kind of more of the same that we started last week with the topographic maps. I'll send that out on Thursday, give you a week or two to finish that as well. So don't get too far behind. Stuff's going to start rolling here in terms of points for your grade for the semester. Up to this point, we haven't had any points, but except for the Mulholland video, but they're going to start coming now, so be ready for that. Okay, you guys ready? All right, we were talking about properties of water last class, and we ended up right about here where we're talking about that water is not compressible when it's put under pressure. So we're going to talk a little about pressure. We've discussed it a little in class. I've asked you several times, are you guys under pressure? And you say yes, and I ask, what's it from? And it's the weight of the atmosphere being pulled down on you by gravity. And that's atmospheric pressure, okay? You're under it right now. You really don't feel it because you're used to it. If you go up in the mountains, you might notice a little less pressure on your ears as you go up, and that's because you actually have a little less atmosphere being pulled down on top of you. When it comes to water, we have something called hydrostatic pressure. And hydrostatic pressure is the weight of a water body being pulled down on top of you. Now, if you've ever done any swimming or diving, you know, if you dive down more than 5-6 feet, you can really feel the pressure on your ears, right? And that's from the water above you being pulled down on top of you. So we're going to talk about how to calculate some of these types of pressure, and then talk about how that pertains to geology and the environment. But to get there, I got to give you a little physics background so you understand what pressure and stress and all this stuff is, because we're going to use that in the coming weeks when we talk about soils and rocks and building things on soils and rocks, which is what humans love to do. We love to mess with nature. We love to interfere with nature. But this way we have kind of a quantitative background. We have numbers that we can compare. So let's get you a little background. We're going to start at the very beginning with the physics. You guys have heard of force, right? Everybody's heard of forces. Anybody know the definition from a physics standpoint for a force? No? That's all right. Force equals ma. That's a pretty simple definition. Force equals m, which is mass, times a, which is acceleration. What does it mean to accelerate? You move faster and faster, right? And if you jump out of an airplane, okay, I don't know how many of you have done that, but if you jump out of an airplane, you accelerate. You know, go from pretty much motionless to gaining speed really rapidly. You do that in your car when you take off from a stop. You accelerate. Your speed gets faster. So if force equals mass times acceleration, we measure mass in kilograms. I know we're mostly true Americans in this classroom who are never really comfortable with our metric system, but a kilogram is a unit of mass. Mass means stuff. How much stuff is there? I am about 70 kilograms in mass. And on Earth, that equates to about 160 to 170 pounds. Now, if I went to Mars, I still have the same mass, right? I still the same amount of stuff right here, right? I would still be 70 kilograms on Mars. But because Mars has less gravity, my weight's going to be a lot less, okay? So weight is the attraction of mass by gravity. But mass is mass. Mass is just the amount of stuff, the amount of atoms that you have in there. So we measure mass in kilograms. And acceleration is a little more difficult to understand because we're changing speed. And in the metric system, one of the units we use for speed or velocity is meters per second. I'm traveling 5 meters per second. And if I travel 5 meters per second all the time, I'm not speeding up or slowing down, am I? I'm just going the same speed. Now, if you're actually accelerating, 1 second you might be going 5 meters per second. The next second you might be going 10 meters per second. The next 15 meters per second. In that case, my speed is increasing by 5 meters per second every second. So that's where the second unit comes in right here. Meters per second squared, which means meters per second. I'm increasing my speed by 4 meters per second every second. So 1 second I might not be moving. The next second I'm going 4 meters per second. Next second I'm going 8 meters per second. Next second I'm going 12 meters per second, and so on. So I'm increasing my speed by a certain number of meters per second every second. And that's written meters per second squared. So if you multiply those two together, kilograms, the mass unit, times meters per second squared, the acceleration unit, you end up with this unit right here, kilogram meter per second squared, which physicists call a Newton. Newton is a measure of force, okay? And you can think of it this way. Let's say I had you come to the front of the room, lie down in front of the desk here, and I took one of those rocks over there. Oh, those rocks, probably 5 to 10 kilograms each, right? And if I held it over your head and let it go, it's going to hit your head with some force, right? We could calculate that amount of force, right? Now, if I did that with a styrofoam block, it's going to hit your head with the same force as the rock. What's different? Just the mass, right? Now, why do things accelerate when we drop them? What's causing things to accelerate when we drop them? Gravity. And here on Earth, gravity has a really set acceleration. We'll get into it in a minute, but it's 9.8 meters per second every second, or 9.8 meters per second squared. If you go to Mars, where the planet is much smaller, much less gravity, it's 3.3 meters per second squared, or about a third of the acceleration here on Earth. Okay? So a Newton is mass times acceleration, and that is a unit of force, okay? So that's the most basic sort of physical parameter we have here. You may have heard about stress or pressure. Pressure, stress, in engineering terms, pretty much the same thing. What is pressure? How's pressure different than force? Think about it this way, okay? I said before I'm about 70 kilograms, right? And the earth is pulling me down right now, right? And I'd be falling if it wasn't for the floor, okay? So gravity is acting on me. I have 70 kilograms of mass times 9.8 meters per second, gravity pulling me down. We could calculate my force, right? But how I distribute the force can be different. And an example would be, I could have you come up here again, lie on the floor, right? And I could step on your head with one of my feet, one of my shoes, right? And your head would feel some pressure, right? Especially if I balanced on your head, right? So that 70 kilograms being pulled down by gravity, and it's then being applied to your head by the sole of my shoe, right? There's some pressure there. Now, is that going to be enough to cave your head in? You're not going to be comfortable, but I'm not caving your head in, right? Now, instead, I put you up here, right? Same deal, but instead of my shoe, I grab one of my wife's high heels, and I step on your head with just the heel. You going to be happy about that? What's different? I still have the same mass, right? Concentrated. What's different? Because in the first case, it's my whole shoe, right? In the second case, it's that little spike on the end of my wife's heel, right? My mass is the same, right? Has gravity changed? What's different about those two? How you distribute the surface area. And you said concentrated. Smaller surface area means more stress, right? And that's what this equation for stress will say. It's force divided by the area that force is applied over. So when we have a really small surface area like a high heel, really small A, what does that do to the stress? Makes it really big, right? Okay, force, mass times acceleration. Pretty simple. Stress is that force divided by the area that you're applying it over. The units, got to think about this a little bit. We said just a second ago that we measure force in newtons, and a newton, you can go and look, is a kilogram times meter over second squared. Now for stress, you take that newton and divide it by meters squared, because that's the unit that we use for area. and do this without screwing it up. So if we have stress equals, let's put force on top, kilogram meter per second squared, and then divide that by area, which is in meters squared. You can go back to your algebra. This cancels out. And you end up with a unit that looks really similar, but it's just one slight difference. You can see here the meter is in the denominator, whereas for force, it was in the numerator. That unit's called a Pascal. Okay, Pascal is a unit of pressure, and that's the unit we're going to use. So a couple of these things are probably new to you. Newton is a unit of force, mass times acceleration, kilogram meter per second squared. Pascal is a unit of pressure, kilogram over meter per second squared. So similar looking, but slightly different. All right, we're going to bring this back to the environment here in a minute, but I just want to make sure that we get our terminology straight. Everybody clear on this? Not too difficult so far. Okay. Now, when you apply stress or pressure to things, they can respond in a number of ways. So I have this eraser that I'm holding up here in the front, right? And I'm going to put some stress on it. And if I do that, you can see it starts to bend, right? It starts to bow. What if I crank on it really hard? I can break it, right? So how a material responds to stress is called strain or deformation. And strain can take the form of bending or stretching or breaking. And sometimes there's no deformation. Okay, I'm up in the front and I'm pushing on the tabletop, right? In fact, my feet are off the ground. Putting my entire weight on this, right? Anything happening at a tabletop? No, a tabletop's sufficiently strong to handle all the pressure I'm putting on it. Now, if that was something that wasn't as strong, you might see it bend, right? And if it's something that's really weak, it might break. Okay? So things can respond by not deforming at all, deforming a little, or completely breaking. So the way we measure this is through a unit called strain. And a strain is a really simple definition. This is the easiest one yet. It's change in length, delta L, over the original length. Okay, this eraser looks to be maybe a foot long, right? Now, if I put it under tension, where I pull it apart and start stretching it, I can change its length, right? I can make it move out. The actual strain is the change in length. So let's say this is a foot. Let's say I stretch it out to 13 inches, right? What's the change in length from a foot to 13 inches? 1 inch, right? What's the original length? 12. So it'd be 1 inch over 12 inches. What's the unit on that? What unit would strain have? What's that? Okay, so on the top, the change in L is going to be in inches, or we're going to use metric, so let's say centimeters or meters, right? And the original length is the same unit, right? So you're going to cancel the units out. This is something that occurs a lot in geology. It's what's called a dimensionless unit. It doesn't have a unit. The units cancel out. I like to think of it as a fraction. In that example I just gave you, it would be 1/12. The strain would be 1/12. Or you can think of it as a percentage. Multiply 1/12 by 100. 1/12 is like 0.08. So it would come out to be about 8%. So I stretch that by about 8%. Think of it this way. This is a foot, right? Let's say I stretched it enough so it'd be 2 feet. What's the change in length? It went from 1 foot to 2 feet, right? So change in length is a foot. What's the original length? A foot. What's anything divided by itself? 1. Okay? What's 1 times 100? 100. So it changed by 100%. It doubled in size. That's what you call doubling, is it changes by 100%. It doubles itself. Okay? So strain is dimensionless because you cancel the units out. So again, think of it as a fraction, or if you multiply that fraction by 100, a percentage. Okay, so here's a little example to get you going. Figure out the tension, or figure out the strain when a 1 meter long rod is subjected to tension and is 1.1 meters afterwards. It's pretty straightforward. I'll give you a second to try it yourself. Okay, so I have this little diagram here that tries to show what I'm talking about. So we have this blue 1 meter long rod, and we subject it to tension. Tension is when the stress is applied in opposite directions. You're stretching something. And after you are done stretching it, it's a little longer. It's 1.1 meters. So the change in length is 0.1 meters over the original length, which was 1 meter. 0.1 meters over 1 meter equals 0.01. So that's the fraction, a tenth, or you can think of it as 10%. So strain is pretty simple. It's just what's the percentage that something changes its shape after it's been subjected to some sort of pressure. Okay, any questions on that? Good. All right, we're going to talk about how water behaves. This is all about water. I'm kind of going off on this little tangent here, and I want to bring it back to water because that's what we've been talking about. And one of the properties of water is its viscosity, how easily it flows. So in order to understand viscosity, we actually have to understand this term right here. And this is kind of what I've been leading to, is something called strain rate, which means how fast does something deform. Now water, if you put it on, let's say, a slope. Let's say you have a slope and you put a little drop of water. That water's going to run down the slope, right? What if I put a little drop of tar or mud up there? Would it move as fast? No, it'd go downhill, but it'd be really slow, right? It has a different viscosity. Well, that rate of movement is called the strain rate. So water and tar and mud and all these different fluids have different strain rates. They deform differently. So strain rate, this is actually really easy as well. It's just the strain divided by the time. And we write it with this E like we did for strain with a little dot over the top. I don't know if you can see that, but There's a little dot right there. So that's the unit for strain rate. Strain is just that little epsilon. Strain rate is the strain divided by time. What did we say the units were for strain? No units, it's dimensionless, right? What's the unit for time? We can use minutes, seconds. We're going to use seconds, okay? So the units, if you have strain rate equals strain over time, and this top unit right here is dimensionless, or no dimension, and this unit down here is in seconds. It's a weird unit, but it's just per second. That's the unit, is per second. And to me, that's hard to that doesn't make any sense to me. Per second. What per second? Well, think of it as a percentage per second. If in that first example, this rod went from 1 meter to 1.1 meters in 1 second, the strain rate would be about 10% per second. Or you can think of it, in this case, as a fraction. It's strained by 0.01, or a tenth, every second. And if I kept at that rate, it would keep stretching by a tenth every second and just keep stretching out. And that's what liquids do. They just sort of keep stretching and moving. Okay, so my guess is that most of you have never seen this stuff before, and that's cool, but you're going to need to go back and look at this, obviously, only seeing it once, and we're going to see this a few more times. So our next chapter that's going to come up in a week or two is going to be on soils, and we're going to talk about how soils behave. There are entire classes on soils. In fact, you can go to some universities and get a degree in soils. We're just going to spend a couple of class periods, but we want to know how soils behave when people mess with them. So we're going to talk about the strain rate of soils. When you add a lot of water to soils, it changes the way they behave. Dry soil behaves differently than kind of wet soil, behaves very differently than totally saturated soil. So the amount of water you mix into soils is going to change the way it strains. It's going to change one of the properties called viscosity. So that's where all of this is kind of going. But we'll get there. Any questions so far? Okay. Give you a practice with this. Okay, here's your first question. And honestly, this is the kind of question I'd probably ask you on an exam. And then I'd ask a follow-up that really gets into the concepts. But just, from a quick standpoint, this might be a typical first-order test question. So you have a rock that's stretched from 2 meters to 2.4 meters in 20 seconds. Figure out the strain rate. Okay, in order to figure out strain rate, you first have to figure out the strain. The strain is the change in length over the original length. What's the change in length? 0.4 meters. What's the original length? 2. So 0.4 divided by 2, that's the strain. Then to get the strain rate, you divide the strain by the seconds. In this case, it's 20 seconds. 0.4 meters divided by 2 meters. Units cancel out. It's 0.2. 0.2 divided by 20 seconds is 0.01 per second. So every second, it strains by 0.01. So after 1 second, it's 0.01. After 2 seconds, it's 0.02. After 3 seconds, 0.03, and so on. Yeah, question?
Will we get these equations on the test?
Yeah, for the test, I'm not into memorizing. I hate memorizing. Mine should not be used as a filing cabinet. So I will give you the equations, but I'm just going to give you the equation. I'm not going to tell you what anything means. So you'll have to be familiar with the equation ahead of time. But yeah, I'll put all this on the exam. I'm more concerned about concepts. So usually what I'll do is I'll say a soil stretch from 2 to 2.4 in 20 seconds. What was the strain rate? And to me, that's worth a point or two. But then I'll ask a follow-up. It's like, and we'll get into this in a week or so, but my second question might be, what if you added 3 times as much water to your soil? Would you expect it to be a higher or a lower strain rate? Well, it'd be a faster strain rate. And the reason, and we haven't got there yet, is because if there's more water, the grains of the soil are less likely to touch and provide friction that would slow down movement. So I'm really looking for the concept, but I'll have you calculate something first. So I want you to be able to quantify the concept, but it's the concept that's really important, and I always give a little more weight to that. So you can even blow the, actual calculation part. If you get the concept right, you still get most of the points. But get the math right too. Math is important. You guys can do this. All right, any questions on the example here? That's about as difficult as I care to get in here. You're not engineers. If you really want to get in this stuff, you can go to School of Mines, take some civil engineering courses, and they'll give you all sorts of really hairy mathematics that will make you cry. They'll also give you a really high-paying job, but we'll talk about that later. All right, hydrostatic pressure. Hydro means water. Static is a term that engineers use to describe something that's not moving. So it's just a static body of water sitting on top of you. So hydrostatic pressure is pressure from burial beneath water. You're being buried by water. So when you dive down into the ocean or into a lake, you're buried by water, and that water exerts its pressure on you. The deeper you go, the more pressure you're going to be under. In this class, we also talk about something called lithostatic pressure. Anybody know what lithos? Rock. So this is being buried under rock and soil. This semester on Tuesday nights, I teach a course on volcanoes. And one of the concepts we talk about in there is called magmastatic pressure. Pressure under a magma body. In all three of those cases, the pressure comes from gravity pulling something down on top of you. So let's just, to understand this concept a little better, let's talk about being buried, okay? So, all right, I'm going to take you out in the backyard. You did really poorly on your first test. I'm going to bury you as a punishment. All right, I dig a hole that's about 3 feet deep, right? And I throw you in it. And then I throw dirt on top of you and fill up the hole, right? So you have 3 feet of dirt on top of you. That dirt is being pulled down by gravity, and you're going to feel it, right? You're going to feel a little uncomfortable. If I wanted to put you under more pressure than that, you did really bad on your test. I really want to bury you. What can I change about that situation to put you under more pressure? I could go deeper, right? So that column of rock sitting on top of you would be deeper, heavier, right? So if I put you down 10 feet, you're going to be under a lot more pressure, right? What else could I do? You want, okay, so let's say I buried you 10 feet deep, but then threw styrofoam peanuts on top of you. Not much of a punishment, right? What's different about styrofoam peanuts versus rock and soil? The mass, actually the density, right? It's not a very dense material. So all those peanuts go on top of you, you're like, yeah, that's all you got, right? So the density, right? But what if I, instead of popcorn peanuts, I put steel ball bearings in there? Those are even heavier than the rock, right? So the density of the material. So we have the depth, the density. There's actually one more thing I could change. Really hard for me to change it. Can you think of anything else that would affect the pressure of being buried? The strength of gravity. I'd have to actually bring you to Mars or to another planet, right, that had more, Mars has less gravity. That wouldn't be much of a punishment. I'd have to take you to Jupiter or something. Big, massive planet with tons of gravity. So the factors that affect the pressure of burial are the depth in meters, the density of that overlying material, and the gravity. And what I've done next to all three of these is I put the units that we use to measure ETH. We measure depth in meters, we measure density in kilograms per meter cubed, and we measure the acceleration of gravity in meters per second squared. Do me a favor and just multiply depth times density times gravity, just the units. What do you get when you multiply those things together, and does it look like anything you've seen today already? So what is depth times density times gravity equal? If you multiply those out and do all the cancellation of units, you should end up with this, which is a kilogram over meter second squared. And if you look back to your notes a couple pages, you'll see that that is the same unit as a Pascal. And a Pascal is a unit of pressure. So it all works out. Pressure, hydrostatic or lithostatic or magmastatic, is just the depth times the density times the gravity. So it's really easy to calculate just how much pressure something is under after it's buried by either water or magma or rock or soil. You just have to know the depth, the density, and geologists measure the density of all these materials. I'll give you some densities for water, for soil, for rock, They're pretty well known. I actually know them off the top of my head because I do this sort of stuff all the time. I don't expect you to. On an exam, I will give you the equation. I will give you the densities, things like that. I'm more concerned that you understand the concepts. So this is how we write it out. So in this case, the stress or pressure due to the hydrostatic column of water above you, stress with a little h for hydrostatic, equals gravity G, depth D, and density. Now here on Earth, the acceleration due to gravity is always 9.8 meters per second squared. That's something you should just know. As an educated person, you should know the acceleration of gravity. I'll probably give it to you on the exam, but you should know that. And then the depth and density is something you would measure or be given. Now the density for water is super easy. It's 1,000. 1,000 kilograms per meter cubed. And if you think about that, think of how big a cubic meter is, right? Meter by meter by meter. So if you had a vessel that was a meter on each side and you filled it with water, it would be 1,000 kilograms. And here on Earth, a kilogram is 2.2 pounds. So that, just think, that's not a big area. That's not a big space, right? A meter by meter by meter. Think of that. If you filled that with water, would you be able to lift it? Would 2 of us be able to lift it? Would 3 of us? Probably couldn't lift it. It's over a ton. It's 2,200 pounds. And rock weighs 2 to 3 times more than that. So if you see a boulder out there that's about a meter, you're looking at 2 to 3 tons. You and your buddies are probably not picking that up and putting it in the back of your truck. And if it's in the back of your truck, it's going to be pressing down on those shocks pretty heavy. So sedimentary rocks are about twice that much, about 2,000 kilograms per meter cubed, or about 4,400 pounds, a little over 2 tons. Igneous rocks are even heavier yet, about 3 times that of water. It's looking at 3.5 tons. So these geologic materials, water, rock, soil, it's heavy stuff. And when it's pulled down by gravity, it creates a lot of pressure. So as you go down in the earth, there's an awful lot of pressure. And you can calculate it. It's really easy to calculate. And here's an example for you. I want you to calculate the hydrostatic pressure at the bottom of a 3-kilometer deep freshwater lake on Mars. Now remember, there's 1,000 meters in a kilometer, so you got to do one little unit change there. I put your equation for hydrostatic pressure. In this case, I guess I did it a little different. I have gravity, density, height. Gravity, density, depth, same thing. And the gravity on Mars is less than that on Earth, only 3.3 meters per second, or per second squared. Okay, what's the gravity? Well, I gave it there, right? 3.3 meters per second squared. What's the density of water? Previous page of notes. 1,000 kilograms per meter cubed. What's our depth? 0.3 kilometers, the same as 300 meters. So you got to keep the units the same, so change it to meters. So 3.3 times 300 times 1,000. If you use your scientific notation, it comes out to 9.9 times 10 to the fifth. Almost 1,000,000 pascals. That's a lot of pressure. Now, if instead you were buried by sedimentary rock rather than water, if you look back at your previous page of notes, it said that sedimentary rocks had twice the density, right? So the only thing you're changing is the density. You're going from 1,000 to 2,000. So you would have twice as many pascals, be about 2,000,000 pascals. And if you're buried under igneous rocks, which is 3 times the density of water, you'd be about 3,000,000 pascals. So you can calculate the pressure with some real basic measurements. Now, the other thing that geologists know are how strong materials are. Okay, some materials will break when under a certain amount of stress. If you had something that breaks at 8 times 10 to the fifth pascals and you buried it at the bottom of the lake, this would be enough stress to break it. The stress is greater than the strength. When your stress exceeds the strength of something, things break. If this was a pencil, it has some strength to it. I start putting stress on it, eventually it bends, and pretty soon it's going to snap. I can exceed the strength of that material. So we will get into some of this, but this is just background for you right now. Any questions on this? All right, I just went through this for you a second ago. Instead of water, we change what you're being buried under to sedimentary rock. The density is 2 times as much. And you end up with twice as much stress, almost 2,000,000 pascals. If it was igneous rock, which is 3 times the density of water, you'd have 2.7 times 10 to the 6th pascals. Okay, we are going to finish up today and next class with how water behaves, and then we're going to move on to soils. So I think we have enough time to get through this today. We're going to talk about oceans a little later in the semester. Most of the Earth's surface is covered with ocean water. We have ocean water in ridiculous abundance on Earth. We don't have fresh water in ridiculous abundance on Earth. In fact, a lot of places on planet Earth are really deprived with fresh water. Go to desert areas, urban areas, there's not enough fresh water for people. In fact, here in the Front Range, we do not have enough fresh water for all the citizens that live here. You guys watched the Mulholland video. Look at the ridiculous lengths that LA went through to get fresh water. Stealing water from 600 miles away through aqueducts, canals. They almost went to war with Arizona. And yet, what is sitting right on the west coast of LA? The biggest body of water in the whole solar system, the Pacific Ocean. But they're not using that water, are they? Because it has salt in it. But we can actually take the salt out of salt water and make that water fresh. Why aren't we doing it? It's expensive. And this is going to tell you why it's so damn expensive. okay? It's a property of water that has to do with how much energy it takes to heat it up. Because one of the ways that we desalinate ocean water is through a process called distillation, which basically means you boil the water, you capture the steam. The steam is fresh water. When you boil the water, the salt gets left behind. You capture the steam, you cool it off, and you have fresh water. But boiling water is one of the hardest dang things you can do in terms of energy. And energy costs money. So you guys have all heard of a calorie, right? A calorie is actually a measurement of energy. The physics definition for a calorie is really simple. It's the amount of heat it takes to raise a gram of water. And a gram's not very big. You guys have seen milliliter of water? That's the same as a gram. It's the same as a cubic centimeter. So think of a little centimeter cube. That's a gram. It's a milliliter. How much energy does it take that little cube of water in order for it to go up a degree centigrade? So it's the energy required to raise 1 gram of water 1 degree C. That's called the specific heat of water. Other substances have different energy requirements. Some things require a lot more energy. Some things require a lot less energy to raise their temperature a degree. Now you've heard of food calories, right? That's actually 1,000 of these. A food calorie is the same as a kilocalorie. Okay? So the food calories we're talking about, not exactly the same as this, is actually a kilocalorie, or 1,000 of these. So keep those two straight. So for what we're going to talk about the rest of class, we're talking about the physics calorie right here. The energy required to raise a gram of water a degree centigrade. So just 1 degree, okay? All right. This, I think, is going to explain why we don't desalinate water through distillation worldwide very much. Has to do with how much energy is required to get that water to boil. All right, we're going to start with 1 gram of frozen water, okay? One little cube, little tiny cube, okay? And we're going to start at minus 20 degrees C. And we're going to heat it up, change it from solid to liquid, and then liquid to gas, and we're going to raise the temperature from minus 20 C to 200 degrees C. Okay? How many degrees are we changing temperature over in this example? 220, right? Now, if you look at the very top of that page of notes, you would think that it should take about 220 calories, right? You have 1 gram, we're going to raise the temperature 220 degrees, right? Actually, that's not the case. Because along the way, not only do we raise the temperature, but we change phase. We change from solid to liquid, and then liquid to solid. And at each of those 2 places, we have to break bonds. To go from a solid to a liquid, you have to break bonds. That requires a whole bunch of extra energy. And even more so when you go from liquid to a gas, you have to break bonds again, and it requires a ridiculous amount of energy just to break those bonds. So let's kind of go through this, okay? Okay, so we're going to start with that little ice cube, that little cubic centimeter ice cube. And we're going to start raising the temperature. We know at 0 degrees it's supposed to melt, right? That's the temperature at which it melts. So let's just get it to that temperature. So we have 1 gram of this stuff. We raise it 20 degrees. How many calories does that take? You have 1 calorie for every degree for that gram, right? So it just takes you 20 calories to get up there. What do you have in terms of the temperature of the material and what state is the material in? We just raised it to 0, right? And so all we did was change temperature. But we didn't add in any heat to break bonds. So what we have is ice at 0 degrees. It's right at the point where it now can melt if we put in more energy. So it only took us 20 calories to go from minus 20 to 0. Now we have ice at 0. But now it's going to melt, right? But in order to melt that, we have to put in enough energy to break bonds. And it's a lot of energy to break the bonds. How much? About 80 calories for every gram. And you know what will happen to the temperature when you add those 80 calories? Nothing. It stays right at 0. And all that extra energy is just breaking the bonds at 0 degrees. Once you add that 80 extra, you then have liquid water at 0. So it took us 20 calories to go from minus 20 to 0. And then it took 80 calories to go from 0 to 0. We didn't even change the temperature. But we did go from solid to liquid. So that 80 calories was just to break the bonds. All right, we have water at 0, right? Now, every time we put in a calorie, what's going to happen to the temperature? It goes up by a degree, right? So we go up, right? We add 50 calories. We now have our water at 50 degrees, right? We had 80 calories, 80 more calories. We now have water at 80 degrees, right? Where's our next phase change? 100 degrees C, right? That's where liquid water turns to gas. So we have to add in 100 calories to bring that liquid water from 0 degrees to 100 degrees. Okay? So to review, to go from minus 20 to 0 required 20 calories. So then we had ice at 20. To go from ice at 0 to water at 0, we had in 80 calories. So now we're sitting at 100 total. To go from, now we have liquid water because we broke the bonds with that extra 80 calories. So we have liquid water at 0. To go to liquid water at 100 requires another 100 calories. We now have liquid water at 100 degrees. To turn it to gas, we have to break bonds. And right here is why distillation of ocean water is impractical. Because we have to break the bonds, right? How many calories do we need to break bonds? It's just a sick amount. 540 calories just to break those bonds. I don't know if you've boiled water on your stove and really watched it. It's pretty easy to get water up to the boiling point, but then you just sit and watch the damn thing, and it just takes forever for those bubbles to form, right? You're just pumping in the heat. And if you actually had a thermometer in there, you'd see that it was sitting right at the boiling point, and that whole time the temperature isn't changing. It's just starting to break bonds. You're starting to get little bubbles, then more bubbles, then more bubbles. And then pretty soon you have a rolling boil, right? And if you plunge your thermometer in there, it's at 100 degrees. It's at 100 degrees till all that water goes. It just sits there and absorbs these energy requirements to break bonds is something called latent heat. When you break bonds from a solid to a liquid, that's called latent heat of fusion. And for water, it's 80 calories per gram. For other substances, it's different. To break the bonds to go from a liquid to a gas is something called latent heat of vaporization. The heat required to vaporize and break bonds. And you can see for water, it's a ridiculous amount. And energy costs money. Energy costs a lot of money. In fact, it's estimated right now that to desalinate water costs about 10 times as much as it does just to get fresh water from somewhere. So that's why we don't use it, because it's so expensive to separate the water from the salt. Well, now that we have steam at 100 degrees, to go to 200, to go from 100 to 200, you just need another 100 calories. So the total energy it takes for that 1 little gram of water to go from minus 20 to 200 is 840 calories. To go from minus 20 to 0 is 20 calories. To break bonds at 0 and go from solid to liquid is 80 degrees, the latent heat of fusion. To go from liquid water at 0 to liquid water at 100 degrees requires 100 calories. But now you have to break the bonds to turn it into steam. That requires the latent heat of vaporization, or 540 calories. Now you have steam, and you're going to raise the steam temperature 100 degrees. That requires another 100 calories. So just to change the temperature is only 220 calories. To actually break the bonds, 620 calories. Almost 3 times as much just to break the bonds. So 620 to change the phase, 220 to raise the temperature. Breaking bonds requires a lot of energy. This is why we don't distill ocean water, because it's really hard to boil water. And if you're ever trying to make some pasta and you're just watching that water do nothing, this is why. Any questions on that? All right, I'll show it to you in graph form. For some of you, this might help. For others, it might not. So this is during heating. So remember, we started right here. We had ice at minus 20. We eventually want to end up over here with steam at 200 degrees. So to do that, we first add 20 calories to get it to 0, but it's still ice. To then turn it to liquid, you need your latent heat of fusion, 80 calories. You now have water at 0 degrees. Now that you have water, you can just raise the temperature of water. So to go from 0 to 100 will require another 100 calories. You now have water at 100 degrees. In order to get steam, you have to break the bonds. And this is where the high energy requirement comes in. You need 540 calories just to break the bonds. And then once you have steam, you're back to 1 calorie for every degree you want to change it. So to go from 100 to 200 takes 100 calories. But you can see that most of the energy is to break bonds, right? The part I like about this is that if you go the other way, it's kind of cool also. Okay, so let's think about taking steam and cooling it off. What happens? Okay? So let's say we start with steam at 200 degrees. In order to cool off, it has to get rid of that heat that it stores. To go from 200 degrees to 100 degrees, it has to give off 100 calories. So it gives it off to the environment. Okay? Now you have steam at 100 degrees. At this point, now if you lose more heat, what happens to your steam? It turns to liquid, okay? In order to turn completely to liquid, though, it has to give off all those calories. And it will. In fact, what it'll do is it'll give off 540 calories. Any of you guys ever had a bad steam burn? Steam burns are the worst. Hold your hand over steam and it burns you. You can leave a really nasty burn. Even though, 100 degrees C is hot, but I've been around lava my whole life. That's what I do. And lava is 2,000 degrees, right? And yet I can be close to lava and not get burned. The reason you get burned so bad with steam is that if you hold your hand over the steam, your hand temperature is only 30 degrees C. It's cold, right? Relatively cold. The steam will condense on your hand. Where does all that 540 calories go? Right into your hand. So all that heat is released into your hand. That's why steam burns are so freaking nasty. Don't get steam burned, it's the worst. And that's because all those calories are being pumped right into your skin. Okay? Now you have condensed water. Let's cool it off some more. We'll bring it down to 0 degrees. It releases 100 calories. This next one's kind of cool. So when I was a kid, my grandparents lived in northern Michigan, and they actually didn't have electricity. And they didn't have a refrigerator or freezer. But they were farmers, so they grew their crops in the summer. But all winter long, they had fresh vegetables. And they didn't get them from the store. There was no store nearby. And yet it was below, way below freezing all the time. How were they able to keep vegetables from freezing? They actually put it under their house. And what they did is they had a little crawl space under their house, and they enclosed it, insulated a little bit. But it's still so cold outside that the crawl space would easily get below freezing. But what they did is every day they would go in and put buckets of fresh water under there. And what would happen is, as those buckets of water cooled, in order to cool, they had to release heat, right? And it released it into the crawl space. And then when water freezes, what happens? It gives off lots of energy, right? In fact, it gives off 80 calories for every little gram. And that would be released into the crawl space. And it would keep it right about at the freezing temperature, just a degree or so above it all the time. And what they really did was made like a little sauna. It didn't feel like a sauna, it was cold, but it was pumping heat into that crawl space from the water freezing. So the water would start to freeze and then release the heat, and it would keep it just barely above freezing for the vegetables. And they were able to keep their veggies from freezing all winter long just by putting water under the crawl space. And it's because water, when it freezes, will give off all this heat to the environment. So that's how water works with respect to energy. It takes a lot of calories to change phase. So that's kind of the take home from this thing, is that to change phase, especially changing it from a liquid to a gas, requires an enormous amount of heat. That's why we don't desalinate water by boiling it. Just too energy intensive. All right, we are going to finish with that. We'll spend a little bit of time next class talking about viscosity, and then we're going to move into soils. So if you have any issues with the physics that we went through today, review it on your own and then bring questions back to class, or send me an email, or let me know if you're having any trouble with it. And we'll see you guys all in the next class.